In the last video, we have started thermodynamics, and in that video, we have made it clear, we understood the terminologies, the terms and their importances and their calculations too, used in first law of thermodynamics. That means we have learned how to calculate changing internal energy of a thermodynamic system. At the same time, we learned how to calculate work done, right? And work done by gas. And what are the indicator diagrams? We have no indicator diagrams. How can you calculate the work done in so many cases? We made it clear. This time, since we have learned that P that is pressure, okay, V that is volume, and T that is absolute temperature. Absolute temperature, temperature in absolute scale. These three physical quantities together are used to define the state of a thermodynamic system. Right? So when we talk about changing the state of a thermodynamic system, right? So changing state of thermodynamic system means actually we are talking about changing the values of these thermodynamic variables. That means when all these three values or two of them, right? In so many cases like this. So if they are changed, right? We say the change, there is a change in state of a thermodynamic process and the operations. And the operations in which the state of a thermodynamic system is changed, right, is called a thermodynamic process. Thermodynamic process. The process is an operation, right, in which the state of a thermodynamic system is changed. State of a thermodynamic system is changed. That means during the thermodynamic process, we usually go to see how the things are changing, how these variables are changing, how this the pressure, volume, or even the temperature is changing. So today we will talk about certain types of thermodynamic process which are popular, and today we will discuss about them in detail and see the other quantities or the things that are used up in first law, how do they work. So during that, let us have the first thermodynamic system, thermodynamic process. So first process is called isothermal process. The first process is called isothermal process. By the name it's clear, iso means constant, thermal means temperature. So it is a process in which temperature of a system T remains constant. T is kept constant. We make an arrangement such that temperature of the system doesn't change with time, even when the other two variables like pressure and volume, they change with respect to each other. But even the third one, the temperature, is kept constant. Let us see like this. Let us realize this in this way. Say we have some gas in a container. We have some gas in a container. A piston, this is container, right? And all these walls are made up of conducting material. So these are conducting walls, right? These are conducting walls. These conducting walls are there. This means they are the better conductor, they are good conductors. They can conduct whatever heat is there from the system to the surroundings. They can do it easily. They can do it rapidly. And say the piston we have. This piston is a light piston, massless piston, theoretical, as well as there is no friction between the piston as well as the body of the gas, right? So there is no friction between the surfaces. And if you place a block, suppose over here, of mass m, right? If A be the area of cross section of the piston, area of cross section of the piston, right? And at that moment, we see the piston along with the block is now in equilibrium, and the piston lies at a height while from the bottom of the container. Okay, so one can easily calculate the volume of the gas. Volume of the gas right now is equals to area A into I, or we call it V initial as AY. Now when this is AY, the volume, and here you can see that the force exerted. Now this block along with the piston is in equilibrium. That means its weight is cancelled out by a force exerted by the colliding molecules of the gas, right? That is, that force for each area is called pressure, right? So we can see what the F upon A, which is pressure of the gas, or this time we may call it initial pressure. P initial is obviously mg upon A. Force mg upon A. This is the initial pressure. Right. Now say, if you gently place another block, if you gently place another block over the first, if you gently place another block over the first block, what will you see? You will see that after some time, slowly you will notice that the piston is coming down, and finally it gets settled at some other place over here. So let me say the initial position of the piston is at 1 and the final position is at 2. 2 is the final position of the piston, along with 2 blocks placed over each other. 1 and 2. So both of them are having mass m. So this is what the new volume of the gas. Yes. If we do that, you will notice that the new height of the piston from the bottom, right? It doesn't remain y, it becomes y by 2. So in that situation, in the second position, finally what we can say, we can see the final volume of the gas. In the beginning we have said, I have told you that the moment you double the load, you make the 2 blocks each over each other, keep the 2 blocks over there, you will see the piston slowly goes down and gets settled at position 2. So final volume of the gas is how much meter? It becomes A into Y by 2, right? This is V final, or V final is equals to AY by 2. That is what exactly AY, and you see is VI. We can say it is VI upon 2. That means in this process we shall notice what? That the volume, the final volume becomes half of the initial volume. That simply means the gas is undergoing a process called compression. So this is what the compression of the gas. When the gas is compressing, at the same time, the final pressure, right? The final pressure, P final will be obviously twice mg upon A, or that will be mg upon A is initial, it will be twice of initial pressure. See, I said what? That if I increase the load, we double the load, we notice that the piston goes down slowly to the point position 2, second position, right? And that means the gas gets enough time, sufficient time to release some heat to the surroundings. That means, and just that by doing so, it does what? Obviously, it does what? It is capable, it becomes capable of maintaining its temperature. So, if the temperature initial was T, obviously in final temperature will be T. Or if you insert through this, if you insert a thermometer, right? If you insert a thermometer, you will notice that the reading remains on the thermometer remains the same. That means temperature is constant. What other thing we do? Yes, to perform this experiment, one thing we have to take care that this process needs some time so that the system can exchange heat with the surroundings, or it can transfer the heat to the surroundings, right? The heat that generated over here is transferred to the surroundings, and just by transferring the exchanging the heat, it becomes capable of maintaining its temperature as a right. So this is what conditions are, that the process must be a slow one. This process should be a slower process. And second thing, that the walls of the container must be an ideal conducting walls. The walls should be conductive, good conductors. they have very high level of conductivity. So this process is actually practically not realized like this. Okay, as the ideal conductor is just a concept. So that one thing is there. And what we notice now, just compare the pressure and volume, the two variables. How if one we have changed what? We have changed the pressure. But as a result of changing pressure, we also observe a change in its volume. And what is that? Yes, just make a list of that. P initial, suppose P, right? And P final is twice P, right? Similarly here, initial V initial is V, and V final we notice is V by 2. Observe the chart. In this chart, one can see very easily that if pressure gets double, the volume is half. When pressure is getting double, the volume gets half. Or even vice versa. If pressure is half, volume will get double. That kind of relation is called inverse proportion, or we can say P varies inversely with V. So for a given amount of gas at a constant temperature, pressure of the gas is inversely proportional to its volume. That means P into V, the product, is a constant. Okay, we can verify this result by our ideal gas equation. From ideal gas equation, what we know? We know PV is equals to nRT, where N stands for number of moles of the gas, N moles of the gas are taken, and when N moles of the gas are taken,